Learning Outcome 7.1. Determine the spectrum of an impulse sampled signal. I've introduced that in the process of sampling, we take our original signal, we multiply it in the time domain by an impulse train that will be periodic, continuous time, and made up of impulses spaced T apart. The sampled signal, xp of t, will be x of t times p of t in the time domain, and its spectrum, through the property of multiplication, will be 1 over 2 pi x of j omega convolved with p of j omega. What does this spectrum look like? You need to know what it looks like in order to analyze what's going on and what the effects are of doing this multiplication. So let's look at our spectrum for our input signal x of t. As in previous videos, we are going to assume that it is band limited. That means that it will have non-zero amplitudes for only a limited range of frequencies. In this case, from minus omega m to positive omega m. I'm drawing it as a triangle, just for making something that's easy to draw, easy to calculate with. And I'm going to say that it has a maximum amplitude of 1. The spectrum from our infinite pulse train is also an infinite pulse train. But now the impulses are spaced omega s apart. And remember that omega s is equal to 2 pi over capital T, this capital T from our time domain. So let's just look at the frequency domain components. And for starts, let's look only at this one impulse and do our calculations with it. That one impulse is 2 pi over t, delta of omega. It's located at 0. We have a 1 over 2 pi, and we have our x of j omega. We can do some algebra and bring our 2 pi over t, which is a constant, to the front. And then we have our x of j omega convolved delta of omega. The product of these two terms is 1 over t. The convolution of these two terms from the sifting theorem is just x of j omega. And therefore the result will look like this, because we're going to take an x of j omega, which had a maximum value of 1, scale it by 1 over t, and we're not shifting it any. Okay, let's look at this impulse and how our system responds to that. Similar procedure, but now we have 2 pi over t delta of omega minus omega s. We're again going to combine our constants and then look at the convolution of these two terms. Our constants yield 1 over t, and the sifting theorem yields x of j omega minus omega s. That's going to put our x of j omega spectrum at a place where omega equals omega s. So that middle spot becomes omega s, omega m gets incremented by omega s, and negative omega m gets incremented by omega s. Make sure you can draw this. Okay, let's try a negative 1 when we're shifting to the negative omega s. Similar procedure. Now where does omega plus omega s equal 0? This 0 here, that's going to be negative omega s. We're picking this whole triangle up and we're shifting it to the left by omega s. So the maximum value will be minus omega s plus omega m, and the minimum value will be negative omega s minus omega m. The maximum amplitude is still 1 times 1 over t. If we consider these all together, we have the spectrum for when we're at the impulse at 0, spectrum for the impulse at omega s, spectrum for the impulse at negative omega s, All of these are drawn on the same omega axes. As to where they're located depends on the values of omega s and omega m. This quantity can be positive or negative. Usually omega s is positive, so this will always be positive. We will likewise have another triangle further to the right for 2 omega s. This omega s would be 2 omega s, this would be 2 omega s, this would be 2 omega s, and we have the triangle here. Likewise, there'd be another triangle further to the right with a 3 omega s and an infinite number also to the left. Draw the pieces out individually. Label all the important points. Then figure out what the values are, and you can determine whether these values are to the left of each other or to the right of each other. And then you can redraw your picture with them in the proper order. We'll do that in the next video and see what some of the effects are.